We're going to start talking about shellcode, and I think we'll do lunch like at 12, like 12 to 1. How's this sound to everyone? And I want to get through a basic example of shellcode by then, and then you guys are going to have a lab where you actually develop your own shellcode. And then I want to get up to that point, introduce the lab to you by the time we leave for lunch. That way, if any of you feel especially motivated, you can have a shorter lunch and work on that over your lunch break. Because that'll be one of the trickier labs, I think. So, it was cool that we exploited this full login program. We got it to run the Go shell function even though we gave it a bogus password. However, it was kind of lame in that we were relying on this pre-existing Go shell function to do our bidding. And that's not exactly arbitrary code execution. Remember I said at the beginning of the class our goal is always arbitrary code execution. That isn't exactly arbitrary because we're relying on this pre-existing code that we didn't design ourselves. We want to be able to cause the program to do anything, to open up calc.exe or bind a shell to a port or something like that. And the process of doing that is shellcode. Essentially what shellcode is a small mini program that you inject into the input of another program, and you redirect EIP once you gain control to that mini program with the shellcode that you've developed, and that mini program will do whatever you want. So examples of real shellcode is something that does like spawning a shell. That's real shellcode. If you're looking at a local Linux exploit, it'll spawn a shell in the root process and it'll have root on the box. Or in the Windows world, it might go to a prefixed web address and download and execute a file there. Most commonly, it's a rootkit or something like that. Or it'll bind a shell to a port, and then the attacker can connect to that port and then issue commands if that's like a remote exploit. What you usually see in like an enterprise scenario when you have firewall set up, you can't, just spawning a shell doesn't do anything because the attacker has no interface to that shell, and just finding a shell doesn't do anything because normally the enterprise is behind a firewall. So common like enterprise attack shellcode is something that will go out and like go to a fixed web address and download and execute an executable, and the attacker will store some rootkit on some hijacked website, and then the shellcode will go and download and execute that shellcode. Or you also see something like connect back shellcode, which is the mini program, the shellcode will connect to a prefixed address, some compromised server, and listen to whatever that server tells it to do, and it'll start reading in commands and executing those commands. And that will sort of bypass the firewall because you're going out, someone isn't coming in. So that's just a couple examples of real-world shellcode. Our first example is going to be Hello World shellcode, because that's the first example for all kinds of programming. But of course, there'll be a different spin on Hello World because it will have to be one of these mini programs, these shellcodes, and that makes it a little bit more challenging than your normal Hello World style program. Okay, so let's talk about some properties of shellcode before we even try to develop some of our own. First of all, it usually has to be pretty small. For instance, programs, even ones to print Hello World, are usually pretty big. If you were to like look at the size of a Hello World executable in Windows or something really simple, that's another trivial program, it would be huge. It'd be like 4 kilobytes, right? And that is bad as a disadvantage for the shellcode because let's assume we're overflowing something like the password buffer. This was only 64 bytes long. So essentially what that means is that our shellcode would have to be less than 64 bytes, okay? And so 64 bytes is pretty small when we're talking about code that you develop. So you always want to make your shellcode as small as possible. Position independent. Usually, when you have a program like Hello World, you'll be passing an address to a function like printf. And so like printf address, and that address will be the address of the Hello World string. So this is a little example to show you guys. If I was to click and write some program, dumb.c, Oops. I did not want to do that. So this is just hello world basically, and you know, C that I just hacked up real quick, and we can see the call to printf is basically just pushing this address to printf, and stored in this address is basically the hello string. You can verify that. So yeah, pushing the address of the string to printf. And this program would not work as shellcode because in this case, they're assuming the hello string is located at this address. It's like a fixed address, you know? And so if this was a mini program, a shellcode that we injected into another process, this address would basically be bogus in the victim process address space. So it would try to print this address. And in the victim process, the process that we're hacking, this address would point to something totally different than hello. In fact, it probably wouldn't be an ASCII string anymore. It would like crash the program or something like that. So your program can't really contain any absolute addresses like this. So when I say position independent, I mean like does not contain any absolute hard-coded addresses like this. So there's another constraint we have to work around, which can be a little bit tricky sometimes. And just to verify my point, see, there we go. I just compiled, you know, the Hello World program. It's like 8 kilobytes, so something really stupid, and there's no way it's going to fit to a 64-byte buffer. So we're going to have to handcraft everything in assembly. Yes, assembly programming. That way we can work around all these constraints because the compiler doesn't normally have to deal with these constraints, so usually you just have to do all this stuff by hand.
I just have a basic assembly question.
Yeah, sure.
So when printf is called,
yeah,
how does it know to use that EAX as the parameter? Is it because you pushed it to the stack?
It's on the stack. Yeah, the x86 and the calling conventions can vary. They're mostly the same in x86. There's a few different calling conventions, but the most common one is that you just push the parameters to the function on the stack before you call them. And printf knows I expect 1 or 2 or 3 parameters, so I'm going to look at 1 or 2 or 3 values on the stack before I was calling.
But it has to be the most recent thing on the stack
Yes.
when you call.
Yeah. So we'll actually talk a little bit more about arguments and that sort of thing once we get into computing depth and new execute stack, because we'll have to understand that a little bit better. That's day 2 stuff. Okay, so just sort of how do you guys visualize the issues we're going to run into with shell coding here? Full screen. Here's another kind of tricky one. Should not contain any null characters. Anyone know why that is?
Just a little bit in the string.
Yeah. So if we're overflowing what's interpreted as like an ASCII buffer, a string buffer, like the password buffer, if there is a null character in our shell code, when the program, the victim program, is reading in our payload, our shell code, and it sees that null character, it's going to say, okay, I'm done reading stuff in, and only half of your payload is going to be copied, or up until when you hit that null character, because null characters signify the end of the string. Everyone got that? A little bit tricky. A lot of times, especially in Windows exploits or vulnerabilities you'll find in Windows, they'll be in like binary protocols where you're not overflowing ASCII data or string data. It's just more like any sort of arbitrary binary data, and you don't have that sort of null character constraints. But just to make your life harder to build character, we're going to say no null characters, because in this class we're generally overflowing string buffers, so we can't have this bad null character. This last point is kind of the same as the position independent, which is basically to say we can't have any hard-coded absolute addresses in our shell code, because they're probably going to end up being bogus in the victim process address space that our mini program is injected into. Okay, So like I hinted at, to basically get around all these constraints, generally you have to handcraft all of your assembly code, if not large portions of it. Write it by hand in assembly, so that is exactly what we're going to do. Luckily for you, we're doing this in Linux and not in Windows, because assembly and internal shell coding in Windows is a lot more ugly than in Linux. In Linux, it's actually pretty nice because Linux assembly program is pretty clean and straightforward. So first of all, before we can talk about writing shell code in Linux, let's just talk about writing assembly in Linux. Out of curiosity, has anyone written Linux assembly code before? Okay, it's no big deal. It's not that bad. So in Linux, hopefully you all have seen at least, you have these things called system calls, which are just like powerful system functions which do things like create a file, delete a file, open a socket, general system functions. So like write, for instance, is a system call. These are just basic general functions that the operating system provides. They're kind of like the core functions that everything else is built on top of. And accessing these in Linux and with Linux assembly is actually pretty easy, which is what we're going to do. For our hello world example, we're essentially going to program assembly to call the write function and then write the hello world message. So write some buffer containing hello world to standard output, which is just 1, and the size of the message. So we basically just have to call that function from assembly, and that's not too bad because Linux has this handy dandy convention where each system function, each system call is assigned a number. So write is assigned like the 1, and create file is like 2, and delete file is like 3, and read is like 4. Those are wrong, but each one is assigned a unique number basically. And then to call a system call, you basically set up the register so that EAX, first register, contains the number associated with the system call. EBX contains the first argument, ECX contains the third argument, EDX contains the third argument, and so on. And then once you have all the registers set up with the correct values, if you interrupt OX80, the operating system will intercept that and say, okay, I detected that this program wants to execute a system call. I assume the registers are set up correctly, and I'm going to use those registers, EAX or whatever, to perform the system call. So it's really pretty simple. Okay, so yeah, I should point that out. So these numbers I was mentioning, I said that each system call has a unique number associated with it, and you can actually find out where these are by looking at this file, /user/include ASM i386 blah 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 .h. I'll bring that up right now. I mean, I've got to tell you what all the system call numbers are in this class, but in case you want to see the other ones.
Is that a standard convention in all Linux system calls that arguments are in the order of are placed in the order of registers? EAX, ECX?
That is for system calls only, not for functions. Yeah. Standard libc functions pass the arguments on the stack, like I was showing you before. They're pushed, but as system calls, you pass the arguments by register. So it's just different because you're calling different things. You're not just calling a general libc function. You're actually telling the operating system to perform some all-powerful function, and the operating system has to handle that. So it just has to be done a little bit different. If you want to learn more about why that is, probably take, I think later talks about that as an intermediate class. I already forgot the name of that file. Can someone tell me what that path was again? It was like ASM i386, is that right?
Yeah.
And then, yeah, so all the unique numbers are there. So you can see that the read is, 3. So if I wanted to call the read system call, I need to set EAX to 3. If I wanted to call write, which is what we want to call to write our message to standard output, EAX has to be 4, open, close, create, unlink, which is like delete file, blah, 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 blah. You can see all the awesome functions that Linux lets us call. And you can call any of these from assembly that you want. Let's say I want to call the fork system call. I can see EAX needs to be 2 because that's the number. Then I would do man fork for the manual page for fork. And oh, this one's pretty simple because it doesn't have any arguments at all. So I would just have to hit set EAX equal to 2 or whatever it was. And then do interrupt OX80. Yeah, question?
Some of those are privileged though, right?
Yes. Yeah. Obviously, you're not going to be able to do anything you want based on what your user privileges are in the system. But it would be up to the operating system to make that determination. You could try, you could like set up a system call and do it, and the operating system would basically say no. And set EAX equal to like -1 to let your program know that you did not execute the system call successfully. So that was actually kind of a bad example since there were no arguments. Let me choose another one. So exit, that one's easy. So exit is system call number 1. And it just has one argument, which is the status. So exit 0 means like there was no, the program executed successfully, or exit -1 meant it terminated the problem. So if I wanted to call this as a system call, I would say EAX equal to 1 and EBX equal to whatever status bit I wanted to exit with. And then I would do the interrupt OX80 command, which I will show you. Yeah. So here's hello world. I suggest you guys follow along with your hand copy of the slides, since like Zeno pointed out, some of this text is a little bit hard to read. So in this case, I create a data section where I store the owned message. Okay, that's what we're printing to the screen. And I'm going to call the write system call just to help myself. I sort of took the manual page entry and put it out here. If I recall correctly, write is number 4 for the system call, so I said EAX equal to 4. Set EBX equal to 1, the file descriptor equal to 1, just 1 equals standard output, basically. And set this parameter equal to the message, the pointer to our string. And then EDX equals 8, which is just the length of this string. And then once I do interrupt OX80, the operating system intercepts that interrupt and says, okay, the program wants to execute a system call, but I assume the registers are set up. I see he wants to do a write system call, those are the things, so I perform it. And there it is, you get hello on the screen. So just to make sure we can all compile and link this stuff correctly, let's all compile and link the basic Hello World shellcode, or the basic Hello World program. This isn't shellcode yet. So these are more commands that you're going to want to write down, by the way. So first off, all of these files for the Hello shellcode can be found in the student home directory. So, and then the Hello shellcode directory, so if you do hello cd, hello_shellcode, you'll see all the files are in there. The one we're dealing with right now is hello1.asm, which just contains what I showed you on the slide. And then to compile and link this thing, write these commands down just so you guys know. NASM, which is the net-wide assembler, -F for format, ELF, which is the Linux executable format. Hello1.asm. And then you also have to link the program. So yeah, I would just add that to your list of helpful commands. NASM, LD, yeah, there you go. So there you go. You know, Linux assembly isn't all that bad. It's actually pretty nice. Once you get into the Windows world, things get pretty hairy. And if you take exploits 2, you'll see why, basically. So I'll just give you guys all a minute to make sure you can compile and run that. So, you know, No surprise there, simple program, easy to compile and run. And the Hello World program at this point is not suitable as shellcode, even though we've handcrafted it in assembly because there are some issues that I'll point out. So first off, let's start looking at this as shellcode and trying to convert it into something we can inject into another process and then point the return address at. Okay, here's another command for you guys to know. And it's objdump-d hello1, which basically means object dump does all kinds of fun stuff on Linux executables, and D is just disassembled. Hello1 is what I named our Hello World, our compiled Hello World executable. And this just will show me the program bytes for our Hello World program and what they actually correspond to in x86 assembly. So we can see that move 4 into EAX, by the way, this is in AT&T syntax, not Intel syntax, just be aware of that. But basically, move 4 into EAX, this corresponds to these opcodes, processor opcodes. Move 1 is this. Interrupt OX80 is these. So here you go. We want to convert this into shellcode, something we can inject into the password buffer and then return into that. So we haven't really tried to make this shellcode yet, but you can go ahead and tell me one thing you may see wrong with this that disqualifies it from being used as shellcode.
The address that's where it's set.
So eventually we will inject our shellcode into like the simple login program or something like that. And this address, the simple login program, is not the same as what it is in the Hello World program, right? This address will probably be meaningless in the Hello World program. And that's because, of course, in x86 protected mode, each process gets its own unique 32-bit address space. Okay, so remote users, remote guys, can one of you point out another issue with using this as shellcode? All right, I'll open it up to you guys again now.
It's got an exit function.
The exit function is not a problem at this point. There's something more obvious.
The null character.
Yeah, there's all kinds of nulls up in here. So if we were to, let's assume that we threw this at the simple login program and tried to make it interpret this as our password attempt. It would say V8 OK, 04 OK, 00 ups, and in the string it would only copy 2 bytes. And obviously we need it to copy like 72 bytes for our exploit to be successful. So those are really the main issues. The exit thing isn't a problem because the exit one is actually a system call as well. And in this case, we're just going to get it to print a message and then exit, and that's just what we wanted to do. So it's no big deal. The main issues here are the absolute address. This address is bogus in any victim process address space, and all these null characters that we got to get rid of. So the easiest thing to do is to get rid of the null characters, actually. So I think that's what I do next. Okay. Oops. You guys, sorry. So for the next phase of the shellcode, we're just going to try to get rid of the null bytes that appear in the shellcode, okay? Because that's kind of easier than dealing with the absolute address at this point. So the reason we got all those null bytes is because we tried to move a value into a 32-bit register. So if you'll recall, in the last phase, this was something like move EAX4. And EAX is a 32-bit register. So when we try to move a value to it, the assembly automatically wants to basically consume the the whole 32 byte register, so it's going to pad out the rest with zeros. Now, there's this cool thing you can do in x86 to address subsets of the EAX register, only other parts of it. So when I say move AL4, I mean don't set EAX to 4, just set the lowest byte of EAX to 4. Let me draw that on the board. This is a little bit tricky. Okay, so in x86, registers are 32 bits, right? Everyone's looking at 50 there. So we have something like EAX. And we'll say these are EAX's 32 bits in their entirety. And let's break it up into it's 4 bytes, okay? Because 32 bits is 4 bytes. Everyone's in there too, right? So x86 actually has a cool way where you can address individual parts of the register. So if you tell the assembler to use EAX, it's going to automatically assume the whole 32-bit register. If you tell the assembler AX, instead of EAX, is just going to address the bottom 2 bytes, the lowest 16 bits. And if you were to say AL or AH, you'd be talking about this byte or that byte. Notice that you can't address these individually. That's just kind of a limitation. You would have to use like a bitwise arithmetic if you wanted to mess with these individually. So if I just wanted to set this to 1, I could just do move AH1. And let's assume that this is like, you know, F, 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 F. The time that I execute this, the end result would be EAX equals F, 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 0, 1, F, F. And then if you were just, you know, look at AH individually, it would still just come out as 1. You guys follow that? Remote users, you okay with that?
Sure.
Okay, yeah, then not too bad. I don't know if there's anything like that in ARM, but that's just kind of a weird thing that x86 does. So, like I was saying, whenever you want to set EAX to a value, like with our Hello World shellcode, we want to do something like move EAX 4, because 4 is the number for the write system function. It's going to automatically, since we're messing with a 32-bit register, it's going to pad this out to be like 00000004. That way it can completely consume the buffer. That's where all these extra zeros are coming from. If instead we did move AL4, it knows that we're just addressing this 1 byte value, so it's not going to add all this extra 0 byte padding. That's how we're going to turn those robots. Got questions?
But how would you, I understand the need to avoid putting zeros up on this code, but
Yeah.
how do you ensure that, you know, the example you gave where everything else is FF,
Yeah.
and you need to have the value of 4, you need to ensure that they're all 0 in the other.
Excellent question. Anyone have the answer to that? So what you should do first is zero out the entire register before you change AL to 4. So you want to make sure that EAX is equal to 0 before you set AL equal to 4. That way the whole value of EAX is 4.
Is there,
But the problem with that is you put in 0, so you have to set FF for FF.
Yeah,
all the way
so,
across
oh,
the
there's a
board.
question. How do we set EAX to 0 without any null bytes? Yeah.
It sets all less and then do an add 1.
You can do that, yeah. There's an easier way.
XOR with itself.
Yeah, XOR with itself. And the advantage there is that the XOR with itself only takes up two assembly, two x86 bytes to represent the XOR opcode with itself. Whereas if you were to try to do like add, or move FFFF and add, that would be many more opcode bytes. And we're trying to keep our shellcode small. So yeah, sort of, you guys already got all that. So yeah, in this case, that's what I did, move AL4, BL1. In this case, the program is already zeroing out those registers for us. Okay, they're kind of assumed to be zero when the program starts there. When we inject it into another process, we're actually going to have to manually zero them out first. But for now, we're just trying to get rid of those null bytes. So you can see if I change it to move AL4, B004 compared to B804 00000. And then the last little trick there is that, how do you get the 0 byte? It's just the XOR with itself. Okay, so null bytes gone. Here's one limitation. Remember the two issues we had when trying to convert this to the shellcode were null bytes and an absolute address. So next we have to try to deal with that absolute address. So the opposite of absolute address is like relative address, right? We have to find somewhere relative to us so we can store this message string. So one sort of data area we can always use that's relative to us is a stack. We can always just kind of add things at will to the stack. So that is how I got around that absolute address issue. I basically push the string onto the stack. So these hex values I'm pushing basically represent the owned message. So I'm pushing the string onto the stack, and then I can just use the stack pointer as a pointer to our message string instead of that absolute address. So that's a little tricky. Probably the trickiest part about this is just understanding the message and the way it's ordered. You can see that owned, I wrote out for my own benefit the way the hex code is associated with this. So owned is equal to like 4F, 77, 60, 65, blah, 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 blah. And I can push it onto the stack in sort of a crazy way because these are represented like, backwards in memory, and the stack is also like rolling down. So there's sort of a lot of real nasty stuff going on there. But at the end of the day, I want ESP to look like ESP to look like this. So I keep always grabbing the one that doesn't work. So stack, rolling down, ESP, and then blah, 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 blah. And the owned message is, 4F 77 6E 6561. So basically, after I push those values onto the stack, I have my ESP register pointing at the owned message. That way I can use ESP, which isn't an absolute address, it's basically a relative address, as the pointer for my message string. I understand the pushes there are a little bit confusing just because of the way I have to order the bytes to get the message in the correct order. But does everyone understand the general concept of pushing the string onto the stack and then using ESP as the pointer? So at this point, when I was developing this class about a year ago, I thought, okay, I should be done at this point. This shellcode should work. I don't have any absolute addresses. If I look at it with the OBJ dump, I see no null bytes, no absolute addresses, everything is relative, it's position independent, everything should be good, but it didn't work. And I spent like probably, I don't know, 30 minutes or something trying to debug it. And can anyone tell me why this still isn't good? What's the issue? There's a bad byte in there somewhere. I'll give you a hint. Can anyone recognize what the bad byte is? It's actually the 0A character. It's the new line character. So what happens is when I had that in my message string, that 0A new line character, which basically is just the new line in my own message, the GETS call that reads in our password attempt sees the new line character and assumes that that means you press enter and are done entering your string. So that's another byte you have to avoid. So what I did was I just changed the 0A character to another exclamation point. Yeah, kind of cheating. And another sort of nasty thing or sort of tricky thing that I did here was that I made the message exactly divisible by 4 bytes. Okay, so it's 8 bytes in total, so length of the string divisible by 4. And the reason I did that is because you can only push 4 byte values onto the stack, so it would have been a huge pain trying to write a message that wasn't divisible by 4, or it would have been more. I should say. Wouldn't be. Let's see now. So I think what we can do actually, well, I just want to make sure this actually works. I put the final version of the shell code in hello 4.asm. So you can kind of see what's going on there. And like Keith pointed out earlier, I went ahead and just exported those registers out to be saved, zeroed out all those registers before I just started changing individual bytes of them. And so this is really nasty looking assembly compared to our original Hello World program, but it should be good as shellcode. And so we can just verify that it still works, which is something you should generally do. And notice we don't get the new line, the message, right? This time is because I just changed it to that extra exclamation mark. So it still works, and when we look at it with that objdump command, objdump-d for disassemble, we can see no null bytes, no absolute addresses, should be all good. So if we were to put this in the password buffer, then override the return address and point it back at the password buffer where this is located, we would actually end up executing this mini program that we just injected into the vulnerable victim process. Which is kind of cool. We've taken one program and basically turned it into another program by exploiting this vulnerability. Okay, so actually, do I have you guys actually? Yes, I do. So that's I'm actually going to have you guys use that shellcode just so you can get a feel for using a shellcode that we know works and exploiting a program before I have you guys develop your own shellcode and use it to exploit another program. So we're going to use that Hello World shellcode that I just showed you to exploit the simple login program. So, to really use this shellcode though, we can see this is the objdump output. We have to sort of recreate these these binary bytes in the password buffer. So remember how we create those addresses like the Perl print \x. We have to do that for these. That way we can just get Perl to generate this mini program for us on command. So I've actually provided you a nice little Perl script to do that. So you can see basically I just took the output of that objdump command. You can see the opcode bytes here in the string as well. So B001 is down here, and then 31db, 8080, because these are just x86 opcode bytes. So if the instruction pointer is pointing at these, it's going to know what to do with them. Because it's programmed to know what these bytes mean. You know that this means interrupt OX80. This means XOR sort of register with itself, and so on. So I just took the output of all this and just turned it into a Perl script to emit those bytes. And what we're going to do is have the simple login program, instead of executing Go shell, execute our hello world shell code. So instead of spawning a shell or printing the wrong password, it's actually going to print our message. And that's significant because we're causing it to execute our own mini program that we custom developed, which means we could, we have arbitrary code execution because of this vulnerability in the simple login program. So everyone understand what we're going to do, the strategy here? So I'm going to walk you through this process so you guys can do it on your own a little bit later. Does everyone understand where this Perl script came from? How it represents the opcodes of the shellcode? For both users, do you follow that as well? Just want to make sure, because I know that that part can be a little bit weird.
Would it be useful to have like a Perl script that
I
punches
know,
that
I know.
object
Someone
up?
asks about that like all the time. And yes, it would be. However, at this stage in your exploit development career, the more suffering, the better. All right?
Okay.
The more stuff you have to, I don't know how to say this to be mean, the more stuff you have to do by hand, instead of going to Metasploit to generate shellcode, doing shellcode yourself, the more you have to do by hand, the more you're going to learn. This is a guided learning experience. It's all about learning. So, yes, in reality, when I'm developing an exploit, I have some magic script where I use Metasploit to automatically generate my shellcode on the fly. But if you really want to be good at this stuff, you have to know how to do all of it manually. Period. So, all right, so it looks like the remote users are still on board. So let's just talk about sort of draw on the board how we're going to generate our payload file, what the stack's going to look like, and then we're going to actually develop the exploit the simple login program. So let's come back to the board over here. Back into stack land. So this is going to be the stack right after the Gibbs call, right after our password attempt has been inputted in again. I'm just going to show you what we want the stack to look like eventually. So essentially, we're going to have our shell code. So say like x31 x c0 x31, so just the bytes, and I'm just copying down off the shell code we got here, blah, 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 blah. The hello shell code is not 64 bytes total, okay? That's only like 30 something bytes. We're going to need to completely consume the password buffer though. So we're going to have some like some padding value in here. So, this is all the shell code. we'll say this is 30 bytes. I'm guessing, I think it's actually something else, but it doesn't matter for now. 30 bytes, which means we would need like 34 more bytes of padding to completely consume that password buffer so we can get to the important process metadata, like the return address and the save frame pointer. So 30 bytes of this, so we'll say like A. And then, so after that, we will completely consume the password buffer. We can just put B's again for the save frame pointer. We don't care about it. And then what will we put for the return address? Can anyone tell me what the return address will be? Approximately? We have shellcode, padding, B's for save frame pointer, because we need to overwrite the return address. Previously, it was like 0804 blah blah AA, which was the address of Ghost Shell. This time, we want the return address to point back into the stack to where our password buffer is, because that's where our mini program is. Okay. So this is going to look, the stack addresses are like BF, so equals F, F, question mark, we'll discover that later. Now, the payload I've described up there actually isn't optimal, and that's because in order for our execution to work, our return address would have to hit the first byte of that shellcode exactly. If it hit anywhere else, like halfway in the shellcode, it would probably crash because it has to execute everything precisely for that shellcode to work. For instance, if we pointed the EIP, return address has to point right here exactly. Okay, if it ends up pointing right here, all of a sudden, well, this would probably crash because it's inside the middle of an x86 instruction. And this would not be a valid x86 instruction because this instruction is technically supposed to start here. Or let's say it started right here, which is valid, but we've only executed half our shellcode, so we didn't initially zero out the registers and we get a crash. So the whole shellcode has to be executed starting at the first byte. So one thing we can do to help ourselves out is using no-ops. So a no-op instruction is a 1-byte instruction that basically does nothing. And what this means is that if we were to make our payload something like so no-op equals OX90 means do nothing. 90, 90, 90, so now, and then put our shellcode here. So let's say our shellcode is 30 bytes. That means we need 34 bytes of no-ops. And then let's put S for shellcode because I keep forgetting what the opcodes are. And this is 30 bytes. Which means these two together are 64 bytes. Which means we'll have no ops and then our shellcode completely consuming the password buffer. then we're going to write 4 B's to overwrite the frame pointer. And what this does for us is the return address can then point at this, or this, or this, or any one of these 34 no-ops, and we'd be okay, because we'd execute one, then the next, and the next, blah, 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 and then start executing our shellcode. Doesn't matter which no-op we start on, because eventually we'll slide down the no-op slide is what they call it, until eventually we get to our shellcode, and we'll start executing our shellcode from the first byte. So what this allows us to do is to have multiple valid return addresses that will cause our mini program, our shellcode, to be executed. And this is critical in exploit development because you want to have a little wiggle room, because often you'll develop, for instance, an exploit for your system, and you want it to work on someone else's system, and their stack addresses will actually be a little bit different. So you want to have sort of like a lot of padding of valid addresses so that there's greater reliability that your exploit will work, because their system is a little bit different than yours. Say they're running source stack 2 instead of source stack 3 or something like that. So having those extra no-ops in there just gives us more valid addresses we can return to and increases our odds of success. Everyone follow that? Remote users, Bedford guys, you okay? There are some in the exploit community that would actually frown upon using no-ops and stuff because they want everything to have surgical precision because it's very skilled. And yeah, there's some argument to that, but when you're trying to develop an exploit that works, you do what you got to do. Okay. So some important points here from this slide, just to reiterate on, is that the no-ops plus the shellcode needs to be 64 bytes. Everyone understands why that is, right? Yep. To completely consume that buffer that we're overflowing, the password buffer. 4 bytes of junk don't matter because we do not care about the state frame pointer at this point in the class. And then the address of the password buffer or the address of one of our no-ops in particular. Because if we can execute one of our no-ops, we'll eventually slide down to our shellcode and be okay. So this is what our payload file is going to look like. It's going to cause a stack to look like what I drew on the board, and then hopefully our shellcode will be executed. So let's go through the process of developing our shellcode. Okay. So first I wanted to see my shellcode in a file. I'll leave those commands up for a second, but you can see that, you know, just put these hexadecimal bytes into this file for us. And this file represents the shellcode. The next thing that we're going to want to do is figure out what the actual size of our shellcode is. I guessed that it was 30 on this, but I think it's something else actually. So you just do, oops, that's not right, sorry. WC shellcode, it's like word count shellcode, would just tell us the number of bytes in the shellcode. So in this case, yeah, I actually got it backwards. The shellcode is 34 bytes, not 30. So that means we need to have how many bytes of no-ops in our payload? 30. And which should come first, the no-ops or the shellcode in our payload file?
Shellcode.
The no-ops. So we need, let's go ahead and start constructing our payload file. The no-ops come first. is there going to be, if you remember when I drew on the board what the password buffer looked like, the P in password was at the very bottom of the stack. And we want those no-ops to be at the bottom of the stack. That way they get executed, the EIP keeps getting incremented and going up towards our actual shell code.
And no up is hexadecimal 90.
90. Does anyone know what no-op actually does?
Yes, it does an exchange.
What register? They exchange what? With what?
With EAX, I think.
Yeah, who was it that said that? Because I know you've taken Dino's class if you know that.
Yeah.
So yeah, we were at super nerd trivia trying to impress girls one night. Remember that? You know, we'll have wild success. So yeah, we want to change EAX, which is basically nothing. So let's start constructing our payload file. First thing we want to do is print those no-ops out first. And we want to print 64 is the size of the password buffer, 34 is the size of the shellcode, so 30 bytes in total, just to make it explicit out that the arithmetic in there. Then I use the cat command just to put the contents of this file and append it to this one. For those of you not familiar with Linux, you might want to write that one down too. So at that point, that's what our payload file looks like, and at this point, it should be 64 bytes. Okay. So at this point in our payload development, we're at the point where we will be overriding the save frame pointer. Okay. We don't care about that, so we're just going to tack on 4 bytes of junk. Now, what should the next value be in the payload?
Addresses, no, so the no-op there.
Yeah, return address into the no-ops, or if you wanted to be fancy, you could try to hit the first byte of the shellcode too. But what is that address? Nobody knows, right? So
Whatever ESP is.
yeah, but where is ESP? So what I want you guys to do is, I'm not going to tell you how, I'm going to see what solutions you can come up here with for a minute. And I use the debugger to try to find out what we should use as the return address for our payload.